Welcome back, everybody. Got a few more coming in. So we're into the final stretch. So we've got 3 more talks now. We're going to do those 3 talks, and then we've got some drinks out the back here and some canapes. I never know how to say it. Canapes? 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 Shows my poor breeding when I say canapes. So we're going to go out there and have some canapes and canapes? Canapes, sorry, I just can't clock it. Canapes. And we're going to see some comedy. So I think you probably all saw my many emails about the comedy that we're doing. So Dave, who's been emceeing, has taught 5 of our cohort, or our sort of cohort and adjacent cohort, a bit about giving comedy delivery of science. So we'll get some drinks, we'll have a laugh, and then we'll watch a few people give some short talks in a comedic style. And then we'll have more canapes and drinks to follow. So our first presenter in this session is Olivier Alard, Professor Olivier Alard, who of the geochemistry at the Australian University node leader of Earthbank. And all I have to do is press on your...
Yeah.
Do you want that one?
Yeah, I don't know. Okay.
You can use that if you pointed at that.
Yes. Okay, and that. Oh, it worked. Okay. So, yes, let's talk about geochronology. And as you know, I mean, geochemistry is highly machine dependent, and it evolved as the mass spectrometer go through breakthrough. So before, and today I will talk about the next step of evolution, which is basically taking advantage of the triple quad or tandem ICP-MS-MS technology. So let's say that's last century geochronology, when you were willing to date some rock, you were basically separating minerals, going through geochemistry, chemistry, I should say, and then using column chromatography to separate one element to another, finally loading it on TIMS, on a thermal ionization mass spectrometer, and then finally you get an isochron like the one up, where you have 4 points. It took you 3 to 4 weeks to get that, about $5,000, and you have only 4 points. Now, thanks to the triple quads, that's the line below, and when you couple it with laser ablation systems, you can get this isochron in less than 5 hours with 30 to 60 points for only a couple of hundreds of dollars, which means that stuff are changing. So, as you know, as some of you know, probably, I'm sure, we use beta decay systems, and the most known beta decay radioactive systems are the rubidium strontium, the lutetium hafnium, and the rhenium osmium isotopic systems. They are kind of harmful because, as you may see, those elements have different geochemical affinities. Some are lithophile, others are what we call high-field strength element, and so on and so on. And of course, rhenium osmium are siderophile and chalcophile. So they allow us to date different processes which happen during rock evolutions. For those who are not geochemists, the peculiarity of the beta decay is that basically one proton exchanges neutron or vice versa, which means that yes, the parents give a daughter element, which is different because it has not the same atomic number, but it has the same mass number, which means that mass spectrometer cannot recognize parent and daughter. So that's why we were going through this painstaking chromatographic separation of the elements to be able to separate chemically the parent to the daughter. But now, with the triple quad, the separation is done like a snap. In 1 millisecond, we are separating the parent to the daughter by just doing chemistry in the machines and by reacting one of the elements of the couple, the parent or the daughter, with a reaction gas. So, for example, with strontium, it's easy. We put usually oxide-bearing gas in it. Rubidium doesn't react with oxygen, but strontium-87 reacts with oxygen and therefore is measured at mass 103, 87 plus 16, while rubidium stays on 87. And therefore, we can measure in situ, without chemistry, all the rubidium, strontium, lutetium, hafnium, samarium, neodymium things. So, since the advent of these techniques, we have kind of expand a lot the geochronology arsenal, and especially with techniques like, of course, all the beta decay systems, such as rubidium strontium in mica, lutetium hafnium in apatite, garnet, rhenium ostium in molybdenite and sulfide, other systems which are in development like potassium, calcium, lanthan, barium, and so on and so on. So nowadays, if you have a rock from the crust, it's almost sure that we can date it with 2 to 3 systems minimums. Uranium lead, rubidium strontium, lutetium hafnium, in garnet, in zircons, in whatever you want. So we are now, one rock will have several ages, and that is what is mostly changing in the view of geochronology. The other things is that I will make the parallel between the drones, the impact of drones on warfare, as we have seen now in Ukraine, and the impact of triple quad ICP-MS. Geochemists are kind of a bizarre breed. To satiate their ego, they want the biggest machine to measure the smallest uncertainties. Now, with the triple quad, it's changing the game because it's a very affordable machine. It's only 400, 500K, and you can do a lot of isotopic systems. So that means that it's kind of re-equilibrating the economic of it, and small lab can do as well as big lab. And that is also an important impact. So because of this affordability, versatility, this kind of machine is producing a lot of data. They are cheap, they are going fast, you don't have to do sample preparation, you are getting plenty of supplementary information which give you a rich data matrix which allow you to interpret all those ages that you are getting. Which means that because we have multiple ages, we need to understand the geodynamic significations. We need also to handle more data but less precise, although I will argue on the precise things. And we need to have a better idea of what is the significance of uncertainty and data dispersion in terms of geological processes. And most of all, we need a new data handling scheme. Something, which is allowing to handle a lot of data of different nature with different size and array. Okay, so here it's an example, for example, from GU, from the Adelaide groups, which have worked on apatite, and he has recognized simultaneously that some apatite have a different Raiber pattern, the type 1 and the type 2, the green and the red, and he was able to date them in uranium lead, a classic one, and lutetium hafnium. From there, I will please go to this paper and read it. They basically build a story about the evolution of copper mineralization. So this is just an example of how you can put all of those data together, both the trace elements, the petrographic information, is the core, is the rim, and the age, which will not be always concordant. And that is coming to one of the most misleading belief of geologists, is that one rock has one age. And that is almost never happening, except for basalts or lava, and usually, and let me ask you the question, is your date of birth define your life? Is that really the most important date in your life, when you were born? Or was it rather when, I don't know, you get a diploma, or when you get married, or when you get your first child? So, like human, rocks are going through iterative and complex processes all over the life. And the date of birth, the age of crystallization, is maybe not the most important age to understand, for example, mineralization in rocks. Now, with these systems, we have access, we can do multiple systems on one rock. And these systems, which are using different elements and different minerals, allow you to get different story, because those elements are different affinities, fluid mobile, some are chalcophile, some are rather refractory elements, different minerals, those different petrology, but also different crystallization sequence, I don't know, stability, pressure, temperature, stability, and different closure temperature. So closure temperature is kind of a very, I will not say dodgy, but discussed and debated concept, but it still has an advantage. It tells us that we are not really doing geochronology, we are doing thermochronology. We are looking at the date at which we pass a certain temperature. So, this is a relatively old study that I did with Michel Moxley and Elena Bedusova about a bunch of granite which were coming from the Mount Isa area, broad area. And basically, as you can see, these two granites have the same kind of mineralogy, but they don't have the same microstructures. And one, the blue one, is associated to mineralization, while the orange is free of mineralizations. So we date the classic zircons with uranium lead, we date the apatite and with uranium lead 2, and then we date the mica and apatite with rubidium strontium. The good things about the beta decay and the isochron approach is that you can have an initial and therefore the composition of the source, adding more information to interpret your data, and that is here mostly anchored by the apatite. So basically we get these two set of ages, and now if we replace it with the broad closure temperature, again, it's something that is evolving and relative. You can see that the two systems, the mineralized and the non-mineralized, have different temperature time thermal evolutions. And one, the orange one, I will say has a normal cooling temperature going relatively quick at the beginning, and then the biotite is the last one, while the others, the mineralized one, show what looks like a thermal reactivation later on, which is shown by the apatite, which seems to have triggered the coarsening of the grain, the mineralization, and the relatively high and radiogenic initial strontiums. So this is only kind of initial study, but it shows the potential of basically mixing all together these systems and doing some thermometry with that. The last one that I want to talk about, and I must say that most of it has been resumed and better explained in the paper of Peter Vermich, which is entitled IMSWD are not the problem, low ones are. So MSWD, which means mean square weighting deviations, is a kind of a rough statistical tool which was used and abused, I think, for years about the statistically meaning of your age, of your data, rather. So the rule was, and it's still enforced today by some reviewer, if your MSWD is lower than 1, then you can trust your age. It's trustworthy age, it means something, it's real age. If it is higher than 1, it's bullshit. Basically, this age is not good. It's not an isochron, it's an aerochron. I mean, this is basically not what MSWD is meant for. First, statistically, it's not a tool which is not true. There is not saying yes or no. Second, what the right question should be, does this age make sense, rather? And in fact, with the triple quad, we are getting larger uncertainty. But in fact, if you look really in detail, each grain almost forms its own isochrons. And this is basically telling you much more than a simple line. The distribution, the spreading, is basically giving you information about the complexity and how protracted are the process in the Earth systems. And instead of removing it, we should work with it, and we should exploit it more. Okay, that's it, I'm finishing. Oh, was I good in time? That will be the first time. So, is the advance of a triple quad a revolution or an evolution? I'm not sure. I would have a tendency to say that it will be a revolution. But what I am sure is that it's a stepping stone. And the geochemists have to evolve for that. And again, I am asking you the questions. Is your date of birth the most important date in your life? That's it.
Thanks, Olivier. We've got time for one quick question, if we have one in the audience. No? All right, I think you're off the hook. I think I can probably safely say my date of birth is the most important date in my mother's life, Olivier. She will tell you that. That's not me saying that, that's her. All right. Oops. All right, our next speaker is Matthias Raiber. Welcome, Matthias. Sorry? Thanks. Oh. Matthias is the Senior Research Scientist and Team Leader of Sustainable Groundwater Futures at CSIRO.
Thank you. Yeah, good afternoon, everybody. So I'm Matthias Raiber. I'm based in Brisbane in the groundwater team of one of the groundwater teams of CSIRO. Today I'm going to talk to you about how we use noble gases, in particular radioactive noble gases, to assess hydrogeological connectivity in Australia. So I first want to give an overview on why is it important to understand hydrogeological connectivity. So I think probably many of you, your primary research focus is not hydrogeology, so I just quickly talk about that. And then I want to talk about how environmental traces are applied to evaluate the hydrogeological connectivity, and that refers both to between aquifers as well as between aquifers, springs, and surface water. And I also want to emphasize how the AuScope project or how the contribution from AuScope was really very important for us to advance the water research in Australia with regards to the radioactive noble gases. So why is it important to understand hydrogeological connectivity? So knowing how aquifers, springs, and surface water systems are interconnected really underpins the effective water management and policy decisions in relation to many, many different fields. So we've heard the keynote address from Brett this morning with regards to significant cultural features, traditional owners, that are very important for traditional owners. We also know for local communities and councils, in particular in remote communities in Australia, understanding hydrogeology, understanding where the water comes from is very important. The same for agriculture, particularly to optimize water management as well as during droughts, and for climate resilience planning as well, also in the transition to clean energy for hydrogen, as well as perhaps also the ongoing hydrocarbon and CSG shale gas industries. It is really important to understand hydrogeological connectivity. So, for example, whether springs or rivers are potentially impacted as a result of these activities. And we've also heard a lot about critical minerals this morning. So, for this purpose as well, we need water, and we need to make sure that we minimize any potential environmental impacts. And again, also for carbon capture and storage initiatives as well. So how do we assess hydrogeological connectivity? So this is a very multidisciplinary approach. So we sometimes like to represent this with this hydrogeological pyramid here on the right-hand side. So the base of this hydrogeological pyramid provides the understanding of subsurface geology, geometry, and helps to identify if there are potential hydrogeological connectivity pathways. So we take into account many different lines of evidence. A lot of what we've heard this morning, for example, geophysics, as well as rock dating or rock mineralogical analysis as well. And we often do that together in collaboration with our colleagues from other research units at CSIRO for minerals or energy, as well as with colleagues from Geoscience Australia and from universities as well. Then when we kind of understand the framework of the system that we're looking at, we look at the top of the pyramid, and this helps us to determine if potential hydrogeological connectivity pathways are likely to form actual connectivity pathways. So there's many different lines of evidence, but one of the critical ones is environmental traces and hydrochemistry. So I'm going to talk most about that in the rest of the talk. So this here on the left-hand side is a conceptual model of the Great Artesian Basin. So recently we started talking more about unlocking the groundwater memory through environmental traces. So that's resulting from some discussions that one of my colleagues has had with traditional owners on Gari, so formerly Fraser Island. When he told them about how we use groundwater dating to understand how old groundwater is, they were very excited, and they said, yeah, so groundwater actually has a memory, right? And I think it kind of makes sense in our mind, right? So there's a lot of information stored in groundwater that we are probably not even thinking about most of the time. So on the left-hand side here is a conceptual model of the Great Artesian Basin with different aquifers shown in blue and different aquithards shown in brown. So the numbers that you see here correspond to different locations along the flow path, one being in the recharge area and 5 being deeper parts of the basin. On the right-hand side here, you can see some of the environmental traces that we use to date groundwater to see how old groundwater is. And similar to the presentation that we just saw from Olivier, groundwater also doesn't necessarily just have one age, so we can have different ages because groundwater follows shorter and longer flow paths. But we have a lot of different tracers. So, for example, tritium and krypton-85 are traces that we can use to identify young groundwater, so up to about maybe 60, 70 years. So we expect them to be present in the recharge area. And then as we go deeper into the system, we move here towards the right, and we come more in the range of older tracers, such as argon-39, which allows us to identify groundwaters of up to about 2,000 years, and then carbon-14, which we can use to date groundwaters about 40,000 years. And then on the right-hand side, where we have these tracers such as chlorine-36, which has a half-life of about 300,000 years, which allows us to identify very old groundwaters. And the same is for krypton-81, so which has a half-life of 200,000 years roughly. And so both of these tracers we can use to identify groundwaters that may be 1 million years old in the Great Artesian Basin, for instance. So at this downgradient flow part of the system, we often have groundwaters that are several hundred of thousands years old or more than 1 million years old. So we have been using tracers such as tritium, radiocarbon, and chlorine-36 for many, many years. So they're kind of our working horses. But more recently, we started using the radioactive noble gases, so krypton-85, argon-39, and krypton-81. And this is very exciting. This is very novel, and Rohan will talk about that more in the next presentation. But there are very few labs around the world that can actually analyze those traces. So krypton-81, for example, is only analyzed at 3 labs in the world. So one is in China, one is in the United States, and one is at the University of Adelaide. And argon-39 is currently only analyzed at 2 labs in the world. So this is quite unique capacity and capability that we have here in Australia. So when we are trying to unlock the memory of groundwater through environmental traces, we also use other tracers such as strontium isotopes, stable isotopes, and hydrocarbons, and so on. So everything that you can see here, and combine it with the tracers that I just showed, the age tracers, and then that gives us the fingerprint of the groundwater. So when we try to identify, for example, the source aquifer of a spring, then we look at the fingerprint of the spring water, and we compare it to that of the aquifers, and then try to figure out from which aquifer the spring is primarily sourced. So that, for example, helps us to answer questions like what conditions existed at the time of groundwater recharge. So we can determine what was the recharge temperature. So, for example, if we talk about groundwater that is about 1 million years old, that was recharged during the Pleistocene, and it might have a significantly cooler recharge temperature than what we have now. We can also determine how long has the water remained underground since recharge, and which kind of rock formations has the water traveled through along its way. And this helps us to identify what factors influence the long-term sustainability of aquifers and springs under changing environmental conditions and human activities. So now, how does the AuScope project, Advanced Radioactive Noble Gases Isotope Research in Australia, in Bayonne? So we only started this project at the beginning of this year, so we're still in the middle of it. But we have already achieved a couple of very important steps. So on the right-hand side, you can see Thomas Chambers from the University of Adelaide. So I should highlight this project is a collaboration between the University of Adelaide and CSIRO, funded by AuScope, and also with other collaborators, such as the University of Adelaide. But yeah, Thomas Chambers has led the development of this automated new radioactive noble gas extraction and purification system. This is only the first of its kind and the second in the world that allows to automate the extraction and purification of krypton and argon from groundwater or from water generally. So we have tried this in 2 different areas, or we have tried this one and the old system in 2 different areas in Australia. One is Gari, that's formerly Fraser Island, so it's the world's largest sand island, and the other one is Hot Spring Valley in the Northern Territory. We have intentionally chosen these 2 very different regions because the conditions there are very different in terms of what we expect the groundwater age to be. But creating this new system has had really a lot of benefits for us. This allowed to cut the sample size from hundreds or thousands of liters that we have to extract from a spring or from a groundwater bore to just 20 liters. So what we now do when we go to the field is we only fill these cylinders, these standard gas cylinders. And this is really important because in particular in culturally sensitive areas, we're not allowed to extract a lot of water. So that really opens a lot of opportunities to go to areas where before we wouldn't have been able to collect these samples. But it also means that it opens these methods to a lot more people, because before it was a highly specialized skill to even collect the samples. And now everybody pretty much can just fill a gas bottle like this with groundwater or surface water. It also enables the detection of ultra-trace radioactive noble gas isotopes. So one of the areas that we have tried this is on Fraser Island, or Gari. So this is a project that was co-designed with the Butchela Aboriginal people and the Burnett Murray Regional Group and the University of Adelaide. So this is a culturally very important place, also an environmentally very important place where we have drying cycles that depend on the connectivity to regional or purged groundwater reservoirs. So in this case, particular krypton-85 and argon-39, but also krypton-81 are very important to supplement other traces that we have used. We expect groundwater there to be very young, and krypton-85 and argon-39 will help to refine the tritium age there substantially. The other case study or trial area where we have tested this, and this is the area where we have first tested a new method where we collect the samples in gas bottles only, where we only collect 20 liters instead of hundreds or thousands of liters, was in the Hot Spring Valley in the Beetaloo Basin. So this is an area where potential development from shale gas occurs, but it's also an area where there are very important, culturally very important and environmentally very important springs there. So we have conducted the fieldwork in close partnerships with traditional owners, and we were guided by the Northern Land Council. So again, in this environmentally and culturally very sensitive environment, it was really critical to be able to minimize the sample volume. So the samples are currently being analyzed for argon-39 by Thomas Chambers at the University of Heidelberg. So he went there to visit the University of Heidelberg for about 6 weeks, and he's currently analyzing them. But I've talked to him last week, and I think the preliminary results show that argon-39 will really help us a lot better to constrain the groundwater age here, because a lot of the samples that we had analyzed were outside the range for tritium, so older than about 50 years, but younger than what we can analyze with radiocarbon. So we had this gap there where we had no suitable tracer before, and this is the gap that argon-39 will fill. So the opportunities are really great, I think, with the radioactive noble gas analysis, but also generally with groundwater dating. I think probably everybody working in the field of hydrogeology will probably agree that the groundwater dating capabilities in Australia are really world-class, but they're also fragmented across different organizations and with probably insufficient capacity and also organizational sustainability. So the proposed solution to overcome those issues is the development of a national integrated groundwater dating capability through strategic investment in infrastructure, expertise, data accessibility, and operational funding, with a key enhancement to improve the measurement capacity and efficiency, and also increase the confidence in groundwater age. So for this purpose, different organizations led by the Australian National University, so the Heavy Ion Accelerator and Radiocarbon Facility, together with UNSTO, as well as supported by AuScope, the University of Adelaide and CSO, came together to develop and submit a proposal to the National Collaborative Research Infrastructure Strategy Fund. So we're currently awaiting the outcome of this, but it would really help us because at the moment a lot of the work is supported by short-term projects, maybe 1 or 2 years, and it's really, as you can imagine, and as probably you know from your own fields of research, it's very difficult to maintain these kind of facilities with very short-term funding. So the other thing that we want to do there is to demonstrate the value of an integrated approach through a case study on Great Artesian Basin springs. And this is something that we're very excited about. So we also, if this funding is successful, we want to work together with the Arabana Aboriginal Corporation in South Australia to really learn more about how we can integrate our scientific analysis of tracers with the traditional owner, historical, spiritual, and cultural knowledge of groundwater and landscapes. And I'll leave it at that. Thank you.
Thank you very much, Matthias. Do we have any questions? Getting very close to the end of the day, we're running out of questions. There's a lot of action going on with the comedians in the room out the back, so there's a bit of energy there. Thanks, Matthias, that's great. We've got one last talk, and our last talk is from Rohan Glover from the University of Adelaide, who will talk about the atom trap trace analysis facility there that Matthias has already talked about. Yeah. There you go.
Hello. That's working. Thanks, Tim. Okay. Good. And thanks also to Matthias for already giving a really good introduction as to why we need these tracers in hydrogeology, and especially how useful the radioactive noble gases are as a tool. So I'm going to talk a little bit about the technique itself that we use to measure them. It's a kind of new technology, and so I think it deserves a little bit of an introduction. And then I guess speak about it as kind of a tool, not just maybe in hydrogeology, but other fields as well. and then say something about our instrument. So I'll just start by acknowledging everyone that's contributed to this project. There's been quite a few over the years we've spent developing this instrument. I also want to thank the various funding organisations, especially the CSIRO, University of Adelaide, the ARC, and of course AuScope. AuScope has supported us with 2 Opportunity Fund projects. The first was really to get our instrument, the first measurements out of our instrument, and the second one Matthias has spoken about already, where it was more about developing the gas purification system and doing some demonstration projects. So I'll throw this slide up first. Matthias already kind of introduced this, but I'll just touch on it a little bit more. These are most of the isotopes you might use in hydrogeology to do dating. So I've color-coded them as to the different techniques that you need to use in order to measure them, and there are various techniques that you do use. On the x-axis, I think, is the important thing here. This is the dating range that they're useful over, right? So very young stuff on the left, tritium, krypton-85, and old stuff on the right. So of all of these, the radioactive noble gases are actually really important because they are chemically inert. They're noble gases, right? So they're not getting involved in geochemical processes. This is really important for a tracer. I guess the other thing is they've got relatively well-known input functions, and underground production is pretty minimal in most cases. Asterisk, but let's just say in most cases, the more of these measurements are done, the more you discover, right? So some research coming out is showing some things like underground production can actually influence some of the results. Anyway, I guess what I want to say though is for a long time these measurements have been very hard to make. Part of the reason is the atmospheric abundance of these isotopes is very low. So this has really limited their application in the past, and the consensus within the community is this new technology, atom trap trace analysis, is the way to make these isotopes more widely used. So a little bit of history. So as far back as the 70s, when radiocarbon and these kinds of things were coming online and becoming more and more used, there were people already talking about the radioactive noble gases and how important they would be in the environmental sciences, especially hydrogeology. So these 2 guys, Hugo Loosely and Hans Uschka, were kind of pioneers in that field, and they were working out of a lab in Switzerland. So what became apparent pretty quickly is that measurement with AMS was extremely challenging. This is because you need a negative ion, you need to create a negative ion, and so I think on a standard mass spec it becomes very complicated, and so the way to do this with a cyclotron AMS system, there's a paper that came out in the 2000s, which is one of the first examples of using krypton-81 as a tracer. It was the study was in Australia, but they extracted about 16 tons of water and got a few tens of counts from their measurements. So that just highlights the difficulty. I mean, this is 30 years after it was proposed, and this is what they're working with. So that's difficult, and then the other way to do this is with radiometry, so just literally counting the decay events as they come along, and you can imagine if you've got a very low concentration to begin with and a very long half-life, you're waiting a long time and you need a huge amount of water. So for krypton-85, there's a few labs that can do this. For argon-39, really the only lab in the world doing this is exactly the lab that these 2 men were working in and where they pioneered that technique. But the only lab in the world and very limited in terms of what they could do because they still needed huge amounts of water. So at the same time, people are working in the atomic physics space and they're looking at the interaction of lasers and matter. And this ends up being a pathway forward. So I don't want to go into too much detail there, but just to point out that there was a Nobel Prize awarded in 1997 to Stephen Chu, Claude Clement-Tanuji, and Bill Phillips for laser cooling. And it turns out this technology is something that we can take advantage of to do trace analysis. And really, I think this is one of the really good examples of an application that have come from this Nobel Prize. So the demonstration using a magneto-optical trap, which is using this laser cooling technique, was a couple of years later to do trace analysis, but it was still almost 15 years before it kind of got taken notice of in the environmental sciences, let's say. So, 30-second crash course in laser cooling. Essentially, what we have, so this is fundamentally the technology that's underpinning this atom trap trace analysis. You have a photon that comes in, it carries with it some momentum. Yeah? And if it's resonant with an atom, it's going to be absorbed and it's going to give that atom a little kick, right? So using a laser, we can kind of push an atom. The atom will then de-excite spontaneously, emit a photon in a random direction, and over many, many cycles, the net force from this random spontaneous decay is zero. So you end up with this, which one? Yeah. This force, which is proportional to the photon momentum times the scattering rate. So how many times you can interact with an atom over some second or something like this, right? And because it's so important that a photon is resonant with a particular transition to have a large scattering rate, this force, is large for an isotope that you tune your laser to, and it very rapidly declines or decays. So it's not sensitive to any other isotopes, and the technique is extremely clean. So we can push, we can have an atom coming in one direction, we can push it with a laser in the other direction, and because this kinetic, we're removing kinetic energy, removing temperature, and this is why we get the kind of term laser cooling. And then we can do that in 3 dimensions, and we get an atom trap. So I just want to point out that laser cooling isn't just for noble gases. It's actually alkalis are the first atoms that were laser cooled. Alkalis and noble gases have the most favorable electronic structure. So this is, what was laser cooled first, but there's a whole bunch in the middle, transition metals, some lanthanides. And this paper is from 2015, this plot. So there have been advances since then. For trace analysis, I guess the noble gases, we can recirculate them in a system so we can build up statistics. So this is an advantage. Metals are sticky, on the other hand, so you can imagine this means maybe we can't take advantage of that, but I think it's really important to point out that there's already an ATAS instrument operating, which is targeting calcium-41. This is a group in China that's doing this, and so calcium-41 has a half-life of 100,000 years and is potentially very interesting for a whole range of applications. So this is maybe something a little bit more recent. So here's 2015, and you can see the interest in laser cooling other atomic species has just increased significantly. So this is just the number of laser-cooled species and the year on the bottom, right? So it's not like we're limited to those things, it's just they're trickier, and so there has to be a really good application. But for the moment, the noble gases are the ones that are most interesting, let's say. So Matthias touched on the fact that there are very few ATA labs in the world. It's a pretty rare capability. It was developed in the US at Argonne National Labs, and they still measure krypton-81 and krypton-85. And the argon-39 capability was developed at Heidelberg University. There's now the lab in China, which is really pushing to do this at commercial scale. They have, I think 6 or 7 of these machines, and they're building another 5 more right here. So they're building this capability at scale as quickly as they can. At the University of Adelaide, we have the capability to measure Krypton 81 and Krypton 85. And we're planning to measure Argon 39. This is kind of in our medium-term planning. The IAEA is also very interested in this technology, and they've got a planned lab in Vienna, which they will be developing, or have been developing for the past few years, but I haven't heard an update on where they're at. This is our instrument. This is what it looks like. Oh, sorry. Is that video playing? I don't think the video is playing. It's all right. So essentially, we're putting a sample in over here. We're using that laser cooling force to collect as many atoms and push them to the detection chamber down here. And this is where we have all of our laser beams in 3 dimensions to form the atom trap. And because it's so isotope selective, whenever we see, or whenever we catch an atom, we know that it's the isotope that we're interested in. And if my little video was playing, you'd see like a nice bright blob right here in the middle when an atom was collected. We can collect 1, 2, 3, multiple atoms in the trap at any one time, and because each atom will kind of give off the same amount of light, it's very quantized. So we can do a counting. It's a counting process. We count how many atoms we see in a few hours of measurement. Our typical measurement these days are about 5 hours. And then we run a reference sample through that we know the concentration, and we can do a ratio in order to work out the concentration of whichever isotope we're interested in. So our machine is now operating. I think that's really important to say because we've been developing it for a while now. A lot of time and effort has gone into that. We need about 10 microliters of krypton gas for a Krypton 85 measurement or a Krypton 81 measurement. And this is important. I mean, Matthias was saying that we're pushing towards being able to get a measurement from 20 liters of water. So you actually only get 1 microliter of krypton gas from 20 liters of water. So at the moment, to do a measurement on our system, you need about 200 liters of water. So this requires still some complicated in-field sampling, but we're pushing towards that 1 microliter of krypton gas. And this is something we expect to solve soon. And we get an uncertainty around kind of like 5%, which is quite consistent with other labs at the moment. Yeah, so on the sampling, I guess Matthias already said a bit about this. So you do have to have some specialist equipment to get 200 liters of water from a bore and do gas extraction in the field. And then we're pushing towards this kind of 20 liters of water, which should make the availability or make it much more widely accessible, let's say. And yeah, we have just had this AuScope project. Again, Matthias spoke a little bit on this. So we do have fully operating gas purification, gas extraction and purification system that's designed to work with those 20-liter containers. So yeah, this has been kind of successful, and thanks to AuScope for the opportunity fund that enabled us to do that. So we have a number of projects with a number of different partners at the moment, and from CSIRO to different universities in Australia and overseas, Queensland Government, Geoscience Australia, ANSTO Defence, these kinds of things. And these are the kind of projects that we're looking at supporting with this instrument, looking at flow and recharge in the Great Artesian Basin, which Matthias spoke a bit about, paleoclimate signals in groundwater. This is something that Woods Hole and Flinders University are interested in. Looking at contamination, this is something, PFAS is a very important thing to get a better understanding of how it's transported in groundwater, and also things like nitrate fluxes from groundwater into river systems. So we have approximately 50 samples to be measured, but these have been collected with the 20 litres of water containers. So the instrument isn't yet able to measure them, but it will soon. So in the meantime, we've been working on doing more projects where we're collecting a bit more gas. So Matthias spoke a little bit about the GARI project, and we have basically a commercial arrangement that CSIRO have organised with a Japanese energy company that we're also doing measurements for that project currently. And just briefly, we also have a new project to develop kind of the next generation ATA, which will allow even smaller sizes and higher throughputs. I think I'm probably at time, so maybe if you're interested in that, please come and see me. Otherwise, happy to take questions. Thanks.
Thanks very much, Ryan. Really exciting to see some of the new technology coming along. Got time for a really quick question, if there is one. We do? Oh, we do. I'll grab it, Ben.
I know that you mentioned that Geoscience Australia is one of the partners that is working on the project, but I just wanted to know if potentially that will, I guess, all this equipment and infrastructure is going to be used for the Resourcing Australia Prosperity Initiative in helping better understand the groundwater resources that we have, but also, I guess, looking at the different stacked aquifers, right? I guess a lot of, when we think about aquifers, it depends who you talk to. I guess shallow aquifers versus deep aquifers. So I guess, is that capability also going to be looking at the different depths of aquifers and the history of the water?
Yeah, I think that's absolutely something that can be addressed with this kind of instrument and these traces. And you're probably going to look at these ones and several other ones to do fingerprinting and things like this. But yeah, looking at connectivity between different aquifers, lower where you might be using water from like a deeper aquifer for some kind of large-scale project, whatever it is, and also interested if that's going to have some impact, say on, I guess, ecological systems, wetlands, or something like this, then yeah, I think this kind of instrument can definitely help in answering that kind of question around connectivity.
Great. Thank you again, Rohan. Thank you, everybody, for hanging around the whole day. Now, we do have some drinks on out the back here. And as I said, in about 10 or 15 minutes, we're going to have a short comedy presentation